And it's 9:05, so we'll get started. Okay, so I'd like to finish today just to say a few concluding words about this topic of vortex rings, and then start on the next thing I want to discuss, which is the motion of, say, general smooth vortex filaments in the 3D Euler equations. And so vortex rings, I'm going to take these off. Vortex rings. For me is the Euler equations. So in a half plane, with the funny, so here H is the set of R and Z where R is positive. And then the diversion condition is modified. And we ask the function to be tangential on the boundary, which really says that in the 3D picture, it's continuous along the z-axis. Okay. And so these are the equations. Let's change this. I'll probably write a bit better with lines. With initial data, say, u epsilon 0, such that the corresponding vorticity is, say, roughly a delta function, or maybe a sum of this. And so we've discussed the first case. We've discussed this in some detail. We've proved it here. And then this is, of course, a harder and, if you like, more interesting situation. So what about the second case? So I won't prove anything. I'll just tell you sort of what to expect, or what's believed and what's known. So we've seen that if, say, if the vorticity, so let's just consider, let me make epsilon thing as being the vorticity for some, for some solution at some time t. It doesn't have to be initial vorticity. If at some time it looks like, say 1 over pi epsilon squared times the characteristic function of a ball radius, let's put a gamma here. So if this is true, and by this I mean that the integral of omega is equal to gamma, and okay, so the okay, well, let me just write it down. And so if I know that the integral, if I know that a vortex is located near a distance r0 from the vertical axis, and if I know it's L infinity, if it scales like 1 over epsilon squared, the maximum height, then we know that the energy will be like, say, gamma. And I believe there's a, how's this go? It's like a gamma times r times log, maybe r over epsilon, plus lower order terms. And so we proved at some point that this is the maximum energy under these assumptions. And then we were interested in initial rate of force this maximum linearly attained, so which the force of the vortice is basically constant. Okay, we've seen that if this is true, then okay, so we proved a theorem, but in the course of proving a theorem, we approximated the Biot-Savart. We needed to figure out the velocity u epsilon associated with such a vorticity. And so we saw that then say u epsilon at a point x was like, let's call this point r naught and z naught, and let's call it x naught. Then the leading order term was really the same as in the 2D Euler equations, and so it was 1 over 2 pi x minus x, or rather gamma over 2 pi x minus x naught orthogonal divided by x minus x naught squared. And then there was a term that was purely pointed in the z direction, and it was like gamma, and so okay, I'm going to be a bit I'm going to sort of cheat here, and so let's say gamma log 1 over epsilon times 0 1, and so this is near x naught with decay away from x naught, and there was the 1 over 4 pi also from and there was a sign that I may have gotten wrong. Okay, so this is the whereas the first term with this the first term is valid not just near x naught, but also as you move away. So this 1 over distance decay is valid more generally. Okay, and so so then let's ask, what if there are several vortices? And so as always, we expect that the first term, the purely rotational term, although it's big, so if at a distance epsilon from x naught where the vortex is concentrated, it's of order 1 over epsilon. It's much larger than the second term, but it's purely rotational. It shouldn't affect the motion of the vortex. That's always what we believe. And so, what if omega is like a sum of gamma j delta x j? Okay, to be consistent. So xj is some r j and z j. So how do we expect it should move? And so so what's the velocity? Near, say, xj. The velocity generated by this configuration of vorticity. And we claim that this u epsilon, we expect. Okay, and so the point is each vortex will generate a velocity field like this one. And so the velocity will be the sum of the ones, the velocity field generated by the vortex itself and the contribution from its peers. And I'm going to assert here, without having done the work to make this assertion, that that the second term, due to the decay, is a lower order term. So if I consider the contribution from the jth vortex at the kth vortex, their distances are rather far from each other, and this will be a lower order term because of the decay of that contribution. And so what I'll say is that the I'll say this should be like this, well, it should be like, say, gamma j x minus xj perp plus this, whatever it is, gamma j over 4 pi log 1 over epsilon, and then something in the purely z direction. And then the contributions from the other guys. And let's say this is lower order. Okay, so here I'm making an assumption, an assertion that if we wanted to prove things, we have to testify. But let's see. So let's look at this. So we believe that the so as always, we'll say this is purely rotational. So it should not contribute to the macroscopic vortex velocity. In other words, it's moving stuff around inside the vortex, but if I'm looking at how the thing moves globally, that shouldn't contribute. You know, okay, again, apologies, this is a purely sort of a hand wavy argument. And so we expected so these should be the leading terms. These should be the leading terms. Okay, and so we would guess that the vortex velocity is so the velocity of the jth vortex. So we expect. Should be roughly, so gamma j over 4 pi times log 1 over epsilon times a unit, just a translation in the vertical direction. And then there'll be, so this is the, this, if you like, is the self-induction of the vortex. This is what we see when there's only one vortex, that it just moves in the vertical direction with a velocity who depends linearly on its vorticity, gamma. And then the other part will be the interaction with other vortices. And so it's over. And there's some signs here which I have forgotten. I think this is right. Yeah, that was right. Okay, and so we can consider different regimes. So there are different so the first situation would be if all of the different vortices, and this should be xj, and I keep on messing up my sub and superscripts. So one is if the vortices are if the distance between them is order 1, if they're not too close together. And then we can see the second term, the interaction term. Well, in general, we can see that the interaction is so that the velocities generated by the second term are of order 1 over the distance, right? 1 over the distance between the vortices. Let's so note velocities generated by this are of order 1 over the distance between the vortices. So I'm tacitly assuming that there's some distance scale such that for every j not equal to k, that xj minus xk is of the same magnitude. Okay, and so there are different cases. So case 1 is if the distance, let's call this is order 1. And then we can see that the, okay, so the translation velocity is always log 1 of epsilon. They're moving fast. The rotational velocity is very slow. And so essentially the interaction is negligible. And what you expect to see is that each vortex moves with its own velocity, 1 over 4 gamma over 4 pi log epsilon, and they really don't interact. And so this is a theorem. This is a theorem of Buta and Marchioro, which was published this year. And so I thought that we might have time to talk about this, but I've decided it's too much, it would take too much time. And I may say a few words about how the proof goes. We can understand the strategy at least. But in some, I mean, so it's harder to prove, but the phenomenon is not very interesting. Each guy just moves with its own internal velocity, and they don't interact much. Okay, the interaction is negligible. So the first interesting case is if the distance. So the point is, as they get closer together, the interaction gets stronger. And so if the distance is like log epsilon to the -1/2, then what happens? Then okay, so then note okay, so then in times so remember we introduced this tau variable, which was a rescaling of the t variable. So in times t of order small 1 over log epsilon, which is tau order 1, we know that the translation distance is like 1. So they move a distance of order 1 in times order times t of order 1 log epsilon, and the number of rotations. So let me imagine I have 2 vortices, just 2, and the effect of the second term will be to cause them to rotate around each other if they have the same sign. And let me imagine that too. The number of rotations. Well, let's see. So the distance is 1 over the square root of log, and the rotational velocity is the inverse of that, square root of log. In general, if I have 2 things, a distance d, and the rotational velocity is 1 over d, then the amount of time it takes to complete 1 rotation will be, so 1 rotation means traveling distance of order d at velocity of order 1 over d. I believe it takes d squared time to travel to complete a single rotation. So the point is, in this setting, 1 over log epsilon is both the amount of time it takes to travel a distance of order 1 and the amount of time it takes to complete. It's the sort of the scale of the time in which it takes to complete 1 rotation. And so this is the first this is the closest, rather the most distant distance at which we see a combination of translation and rotation in timescales of order 1. I mean, if you look at so this is a setting where you might see the so-called leapfrogging. Right, so leapfrogging means at the same time you see the center vorticity of the whole set of things translating, and then some non-trivial motion of the vortices around the center of rotation. So in the case of 2 of the same sign, rotation. Okay, and so and note also if I have, and I can imagine between cases 2 and case 1, you can sort of, well, you can kind of interpolate. There's a case 3, which is the distance is like log epsilon inverse. And so here the, in some way this is easy. And so here the translational velocity is 1 over log epsilon, and the rotational velocity is 1 over log epsilon. And so, so this is where, the 2 things are of the same order of magnitude. And so this says, well, you'll see both translation and rotation, but you'll see in say times of order 1 over log epsilon squared, I guess, you'll see order 1 rotations and a small translation. So but so the velocity is the same, but it takes but a rotation is accomplished more quickly than a translation on an appreciable scale, because to compute the rotation, we have to travel distance or 1 over log epsilon. But you can also call this leapfrogging if you want. You can call leapfrogging anything in between here and here. And then case 4 is if the distance is appreciably smaller than this log epsilon inverse, then the rotational velocity is much faster than the translation. And to leading order, you would see the vortices standing still. I mean you wouldn't see no translation at all while they rotate around each other quickly. And so this is what we expect. And so the only theorem is case 1. And well, then there's a theorem that's been announced in this meeting last week, a construction of solutions in case 2. And I should say case 2 is a theorem for the Gross-Pityevsky equation of myself and my friend Didier Smits, which we also won't talk about. So, okay, about the Buta-Marchioro proof. So as usual, there are a lot of sort of messy details, but we've seen enough of this to understand the sort of philosophy and the issues. And so they're considering, let's draw a picture. Let's at least have a mental picture. They're considering this axisymmetric Euler equation on the half plane with, say, let's imagine there are 2 vortices, and they're rather far apart from each other. Their distances are order 1, and so we expect that the interactions will be much smaller than the force that gives rise to their intrinsic velocity, the self-induction velocity, and so they should, and so the smaller one would move faster and overtake a slower one, and so on. Our goal is to prove this. So what they do is they so the idea, so the plan. What they do is they try to follow the Marchioro-Polveretti proof from 30 years before of the dynamics of vortices on the plane. And so they want to consider a single vortex in a background flow right? So as we did with in the 2D setting. And so I imagine, I start with these two vortices here and here. I imagine them as, each of them is supported in Bolliger's epsilon. And I write the Euler equations as a system. I say there's a U1 generated by omega1 and U2 generated by omega2. And each one, and so U1 will solve the Euler equations with background force in terms who are exactly coming from the velocity generated by the other vortex, and vice versa. And so, and so if, as before, if you can prove, and so also I should say, and so the assumption would be that the background flow. So I want to imagine that these guys are distance order 1 apart. So the background flow should be, I can estimate how big it would be order 1, in fact, if according to the heuristics I just sketched, and Lipschitz is continuous and so on. And so that'll be true as long as you see if these vortices develop little tendrils that reach out and interact with the other vortex, then it becomes harder to then we can no longer assume the flow generated by this guy is Lipschitz continuous in the neighborhood of this guy. So the main point is, so the goal, okay, so so we want to know that in the background flow of order 1. So the goal is to show that in this setting, the velocity of the vortex is, well, 1 over 4 pi log 1 over epsilon times 0, 1 plus O of 1. Okay, so the background flow introduces a small perturbation that doesn't change the velocity much. We actually know how to do this. We can do this already. We pretty much did. And then the other part is to show that the we have to control the spreading of the vortex, the growth in the radius of the vortex core. And remember, this was the part that occupied most of our energy in the previous proof. And so there the first step was, we said we had this nice, beautiful, elegant computation, wasn't too hard, where we said look at the we said consider the second moment of the vorticity about its center vorticity, and we computed the rate of growth of that quantity in time, and we found that that satisfied a differential inequality. We so this is the integral of x minus some x epsilon squared multiplication of the vorticity, where x epsilon was really was the center vorticity, so this is depending on time. We differentiated that and we found that quantity, let's call it I of t, was bounded by a constant times I of t. And so then we used Grommel's inequality and said that at time, at a subsequent time, it's maybe e to the c at a subsequent time, we say capital C, would be e to the ct times its value times 0, which was small. Okay, and so the first step was the growth control the growth of the second moment about the center of vorticity. And the big difference here is this doesn't really work. Let's just say it doesn't work. So, and this is because we're not working with because the Biot orthogonals change. Instead of being the logarithmic or this nice symmetric thing on R2, it's that thing plus lower terms, and those lower terms just destroy the computation. And so what they do instead is they instead rely on on the vorticity concentration lemma that we already used quite a lot. And so that tells you that that gives you a much weaker information. So this second moment bound says that the second moment is order epsilon squared. Good, it's small. So this is much weaker. So we would want, so before we had but that doesn't work. And so the vorticity is concentrated. Well, so what we saw is that so what these concentration results say is that, well, if I look at a ball of radius in the last theorem, the way we use it was what was it? If I look at a ball of radius epsilon times log epsilon, well, that contains most of the vorticity. It contains all but 1 over log epsilon, but it's you get all these logarithmic factors appearing, and if I look at a ball of radius square root of epsilon, that contains all but 1 over log epsilon of the vorticity. And so here you get errors. And so roughly speaking, these would give you sort of concentration with errors of order 1 over log epsilon, which is a lot bigger than epsilon squared. And so the information you start with is a lot weaker. But then sort of nonetheless, though weaker, one can nonetheless repeat the earlier arguments with some difficulty. It's not that hard. It's just sort of technical. And so let's remember the earlier arguments. The earlier arguments were, well, we wanted to control the basically we wanted to say that we started with just concentrated in the ball of radius epsilon. We want to say that for a while it remains concentrated in the ball of radius square root of epsilon or something a bit bigger. And so to do this, we looked at we defined a quantity which was sort of a smoothed out version of the amount of vorticity outside a certain ball of radius sigma. R, I forget what we called it. And so we looked at that quantity. We tried a difference in inequality. We controlled that by the amount of vorticity outside a slightly smaller ball. And the same thing is done here, and it's by the same kind of computations, and you just have to work harder because, and again, when you use the fact that the BOSR kernel in this axisymmetric without swirl setting to leading order looks like the BOSR kernel on R2, but then you have to deal with these other terms, the terms that reflect the axisymmetric geometry. And so that's the proof they do in this case 2, what I call case 2, no, case 1. And that's how it goes. And so we can imagine spending a week or two and supplying those details. But instead, I had to move on to a different topic. So let me see. So we will not do this. But the point I want to make is, well, there are 2 points. The point is, one point is that we already understand this whole field well enough that we can see what the issues are, what you have to do to prove it, and the kinds of things you have to confront. And the issue, and so the basic one is we're trying to reproduce the earlier proof. The more complicated and unpleasant form of the BOSR kernel in this setting makes that impossible, and that causes the proof to break down at certain points. We substitute ingredients that we're already familiar with, and so on. Okay. I feel like I lost my I feel like I lost my Golden Gate background, but so we won't do this, we'll imagine. And so the next point is, suppose I want to prove something about leapfrogging. Well, then one thing I could do is I could go back and say, here's case 2. Let's try to just drill in a bit deeper and see if I can use the same techniques to do this. Apparently, Marchior and Buta, they actually, I'm not sure if they had in mind case 2 or case 3, and so these are different things that one could both call leapfrogging. In that so leapfrogging is again a combination of this translational motion and some interaction on time scales, in which you can see both phenomena doing something non-trivial. So let me see. Anyway, that's just hard for reasons that we discussed at the after the end of the hour last time. Okay, so then that's all I will say about vortex rings, unless there are any questions. And so then, if not, then the next topic is say general vortex filaments. In R3. I got these new glasses, which were supposed to be better than my old glasses until the real ones arrived. But I said, I told them, look, I need them now, make them quickly. And so in particular, the old glasses had, they were what's called progressive glasses. They had sort of reading glasses in the lower half and a distance vision in the upper half. And these ones, I said, look, forget that, just make them quick. And so I don't have the reading glasses down here, which is why I still can't read, which is all I ever actually need to do. So, okay, too bad. But okay, so we talked about this a bit a long time ago, and so I'd like to start by giving a kind of a heuristic discussion. So here's a formal discussion. So let's imagine I have some u, and so for now, let me not think of the time variable. Let me just think of things that's being a function of x. Actually, I don't want to write arrows. That'll kill me if I do that. And maybe let's put epsilon here. I want omega epsilon to be roughly, we discussed this a while ago. Let's see. Concentrated in that epsilon tube around the smooth curve. Gamma. And well, let me tell the prototype, which we also discussed a while ago. So the prototype. Let's first consider epsilon equal 0. And let's say gamma is a periodic curve with length L in R3. So I can write that as a curve from R mod LZ to a map to R3 such that, and I'll call the variable S ds gamma is equal to 1. So that says I have an arc length parameterization. And let me always assume that gamma is injective. And let me distinguish between the parameterization little gamma, and let's say capital gamma is the image of little gamma. Okay, and so then the prototype, then the ideal vorticity is, let's write it as omega sub gamma. This would be a measure. And so a vector value measure defined as follows. And so if I want to tell you, if I want to define a measure, I have to either tell you how it acts on sets. So I can a measure is a set function that acts on measurable sets, or I can tell you how it acts on functions. And let me do the latter. So and let me tell you how it acts on vector fields. P dot d omega gamma is the integral over. So again, R mod LZ means the I'm considering periodic functions with paired L on the real line, and so integrating over R mod L is the same as integrating from 0 to L if I like, from minus L over 2 to L over 2. Over any interval length L, and then we'll look at phi of gamma of S, and then you have a dot product with gamma, the derivative ds. Okay, and so that's the measure, and I can see that this it's supported on the curve gamma. So if phi vanishes on the image of little gamma, then this will certainly be 0, the interval. And I can see also it's I can think of it as being tangent to the curve little gamma in the direction given by the parameterization. Okay, and so capital gamma is not just a curve; it's an oriented curve with the orientation given by the parameterization of the gamma. With orientation, and then the ideal velocity is, well, I would just apply the BS of R kernel to this, and so that's K convolve with this omega gamma. And that's, if I remember the kernel correctly, that would be, say U of X. So I would have, I would look at, I'll write some stuff and erase it. Well, actually, I won't. Okay, I would do this. D omega gamma, and I would integrate respect to the exponent variable. And let's write down what that is, just from the definition above. This would be the integral, say, from minus L over 2 to L over 2 of 1 over 4 pi. And so the recipe is I just replace x prime by gamma of S. Okay, so this is the ideal velocity field generated by a curve gamma. And this, of course, is not, as we saw before, it's not even locally in L2. And so the Euler equations just don't make sense at all for this velocity field. And so the epsilon regularization, so say the epsilon regularization, so let's say the prototype on epsilon vorticity, would be, well, I just take the earlier singular thing and let me regularize it by convolving with a modifier. Say omega epsilon gamma is, I'm not put this arrow here, but I did. Is, say, eta epsilon convolve with omega gamma, where eta epsilon is a symmetric modifier. And I want it to be radial. Okay, so this is the, so I'll just take my singular vorticity and regularize it in the nicest way I can. And I may as well assume that, you know, if I want, I can assume that this is true, that the gradient is bounded by constant over epsilon f4, etc. Okay, so and then the prototype epsilon velocity is just the Biot-Jerrard kernel applied to this omega epsilon gamma, and let's call that u epsilon gamma. Okay, and I want to understand this. I'm sort of repeating some of this from a month or two ago. And so, so here's what I want to do. I would, and so I'd like to say, remember that for a solution to Euler equations in any number of dimensions, the velocity is, sorry, the vorticity is transported by the flow. What this means is a bit different in 2 and 3 dimensions. In 3 dimensions, so recall, well, actually, let me first draw a picture. So here's the curve gamma. And then there's some tube. Around gamma. A tube of thickness epsilon. So gamma, the vorticity in gamma has, you know, it has a direction given by the direction of the parameterization. And so I think it was being sort of infinite on the curve and pointing in the direction I'm indicating here. When we regularize it, we'll get something who lives, let's smear it out. Who lives here? It's still pretty big. It'll be order 1 over epsilon squared, I guess. So that's the picture we have in mind. Okay, and so okay, and so I want to then, and so I want to recall that omega. So if I now imagine I solve the Euler equations for a solution of Euler, omega at time t. Well, I would look at the flow map, and so that's given by the. If I look at the vorticity at some point alpha and at time 0, and then at time t, I both transport that to the new point x of t, and then I have to multiply it by the gradient of x, the gradient of x alpha. Okay, so there's a more complicated relation, but nonetheless relation between the vorticity times 0 and time t. In particular, this says that, so the support of omega at time t is contained in the image of the support of omega at time 0. Okay, and so if I want to know, so in principle, if I want to know how the whole tube is evolving, I just have to know how the boundary of the tube is evolving. Well, let's say, so to understand the tube motion, I only need to understand the motion of the tube boundary. And we're out of time, but that's what we'll do next. And so there's a sort of a formal computation that gives rise to this famous binormal curvature flow that I've talked about. So I'll describe how that goes. And then I'll give it, so this is an open problem, it's a hard problem. But I'll say what's known about it. And also the binomial flow has a lot of interesting properties, which we'll review quickly. So I think that's about all I have time for. Yeah, that's all I have time for. So I can't stick around. I can stick around for like a minute or two today. But if there are any questions, as always, I'd be happy to answer them quickly today. So and so my plan now, what I think I can realistically do in the rest of the semester is finish this, is discuss this, is to give the little that's known about these vortex filaments in 3D and the Euler equation and the binomial flow. And then I'll talk about the Gross-Fidesi equation a bit in the remaining time after we're done with Euler in 3D and binomial curvature flow. And so I don't know how much time there's left in the term, but that'll be like 2 weeks in each topic, maybe 2, 3.